Good morning. This morning we are going to be talking about probability, giving us an overview so that we can access the UCAT questions that are taking us through probability. So, before we get going, who am I? My name is Nick Featherstone. I am the Assistant Head of Maths here at My Headspace. I'm rocking a master's degree in mathematics, a master in maths, and I've been teaching for up to 14, 15 years now in a variety of positions across a bunch of different establishments, leading schools around the country. Right, having said that, let's talk probability. Now, probability is actually quite intuitive. It does very much what you think it should. So here I've listed out a sort of definition. The probability of something happening is the number of favorable outcomes divided by the total number of possible outcomes. So when I do something that's random, one of a number of things will happen. I roll a dice. I could roll a 1, a 2, a 3, a 4, a 5, or a 6, for example. I pull a ball from a bag with 3 red balls and 7 blue balls. I could pull out a red ball, or one of 3 red balls. I can pull out one of 7 blue balls. So let's have a quick look-see here. When I'm pulling a red ball, pulling a ball out of a bag, and there are 3 red balls and 7 blue balls, the probability of drawing a red ball is. Now, how many balls when I pull out would be favorable for me? Well, there are 3 red balls, so there are 3 outcomes that favor me. 1, 2, 3 possible red balls. How many possible things could have happened? Well, I could have drawn out one of 10 balls. So it's a 3 in 10, which is a way that we use very naturally to describe probabilities with fractions, 3 chances out of 10. We could also write that as a decimal, 0.3. We could also write that as a percentage. We will see that quite often, a 30% chance. Rolling an odd number on a dice, P brackets odd number. You'll see this notation a lot. Capital P, not lowercase p, capital P, and then the event. An event is a collection of outcomes, is a thing that has happened. So if you roll a standard 6-sided dice and you want to roll an odd number, how many outcomes are favorable? Well, 1, 3, 5. You could roll a 1, a 3, or a 5. There are 3 favorable outcomes out of how many possible outcomes? You could have rolled a 1, a 2, a 3, a 4, a 5, a 6. So we are looking at 3 out of 6, which we can simplify to 1/2. We could also write that probability as 0.5. We could write it as 50%. It's 50-50. Probability of being correct, when you guess the number that someone's thinking about and they're thinking of 1 to 10. Well, they've thought of their number. That's in place. All right, so I'm asking Dav. Dav has thought of a number. How many correct numbers are there between 1 and 10? Well, there will be 1 correct number out of the 10 possible ones I could have chosen. So that is a probability of 1/10, a 1 in 10 chance of success, 0.1, 10%. Now, before we move on any further, for an essential here, this is a personal one of mine. A probability of 3/10 doesn't mean that you will draw a red ball like on a regular 3 out of 10 times. That's not how it means, right? If I try pulling a ball from this bag and putting it back 10 times, I will not get the red ball 3 times exactly. I might not. But what a probability of 3/10 means is if I try this a lot, not even 100 times, like 1,000 times, 10,000 times, the proportion of times I get it correct should be about 3/10. All right, but we are talking a lot of times. Okay, so that's important to understand. The probabilities are not a guarantee. All right, they say if you try and do this a lot of times, and I'm talking a lot, that's the proportion of times you should get it right. So one thing to talk about is probabilities must add to 1. All right, why is that? Well, something has to happen. Okay, probability of a red ball. Well, let's have a look. What's the probability of a blue ball? Okay, well, that is 7/10. There are 7 blue balls. Probability of an even number will also be 1/2. And the probability of being wrong in part C, well, there are 9 incorrect numbers out of 10. You will notice that when you add them, 3/10 plus 7/10, you will get 1. 1/2 plus 1/2 is 1. 1/10 plus 9/10 is 1. Now, why is that? Well, something has to happen, right? If I list out all the things that are favorable and all the things that aren't favorable for me, then I should have listed everything out. So if I list out all the favorable and unfavorable outcomes, I will have the total outcomes. So having said that, can we find the probability of an event not happening? Well, very easy. If the probability, now we will also, in probability theory, instead of just saying probability and writing out a whole sentence, we tend to use capital letters. So A represents an even number, a red ball falling down the stairs, whatever it is. The probability that A happens is 2/7. The probability of it not happening is 5/7. Why? Because together you will have listed out everything that could have happened. So you should have everything possible out of everything possible. They should add to 1. So if B happens with a probability of 17/18, not happening 1/18, 0.55, 0.45, 98%, 2%. Okay? Because something either happens or it doesn't. Once you've listed all of that out, you've got everything listed, you should have a total probability of 100%. You are guaranteed that something either happens or it doesn't. All right, let's try a few things out here. So here I've got an illustration of an entire deck of cards. All right, 4 suits, spades, hearts, diamonds, clubs. 2 of them are black, 2 of them are red. We've got the numbers 1 or ace to 10, and then jack, queen, king. Those of you unfamiliar with the deck of cards. So if I draw a card at random, the probability of drawing, I don't know, a king. There are 4 kings out of 52 cards, which simplifies to 1/13. The probability of a black 5. Well, there are 2 black 5s out of 52, which is 1/26, for example. The probability when I take a card at random of drawing a 3. Well, there are 4 3s out of 52 possibilities. That is also 1/13. All right. The probability of drawing the ace of spades is there is 1 ace of spades in the pack out of 52. This is what I mean. Probability functionally is incredibly intuitive. All right. Now we're going to throw in a bit of terminology in here that's important for us. So we're going to start with, what if I toss a coin and throw a die? What is the probability that I land on tails and a prime number on the die? Well, let's have a think. What we can notice here is we can deal with these two things separately. So first of all, what's the probability of landing on tails on a fair coin? Half the time that will happen. Now, within that half the time, so we've already got a half, right? Half of the times I do this, overall, if I do it a lot of times, it will land on tail. Then we roll the dice. Now, of that half the time where it lands on tail, what proportion of times will I get a prime number on the dice? So prime numbers on dice are 2 and 3. 1 is not a prime number. So that is a 2 and 6. All right, because we are taking 2/6 of 1/2. These two things are completely unrelated. So this actually gives me 1/6 in total. These two events are independent. All right, because the idea is the probability of the dice landing on a prime number will be 2/6 no matter what happens to that coin. The coin does not influence the dice. Now we're going to add a little bit of notation in here, which you will see from our Venn diagram video. So if A and B are independent, the probability of A and B, we recognize this from our Venn diagram, is just going to be the probability of A times the probability of B. Okay, this is what we call independence. So if I select 2 cards at random from a deck, what is the probability that I select a king and then any diamond card? Now, you could be forgiven for thinking, well, the probability of selecting a king is 4/13. And then we need to pull a diamond card. Well, there are 13 diamond cards out of 52. Well, except this isn't true. The property of pulling a king is 4/13. That is true. However, once you've pulled that king out, what is the probability of getting a diamond card? Well, this depends. Because if you pulled out the king of diamonds as your diamond, so if you pulled out the king of diamonds, then there won't be 13 diamonds left in the deck. All right. To be fair, whether you pulled out the king of diamonds, so if that first card is a diamond, so either the first card isn't a diamond, in which case there are 13 left out of 51, right? Because you've already pulled the card out, but you could have pulled out a diamond, in which case there are only 12 diamonds left out of 51. And which one is it? Is it the 13 over 51 or the 12 over 51? It depends. All right. Which number I use here depends on what happened in that first instance. When I pulled that first card out, did I, trying to get a king, did I pull out a diamond or didn't I? And dependent on that, that will change the probability of a diamond on my second card. These events are dependent. Okay? Because this probability changes. So we can't just randomly multiply these two things. We have to think a bit more carefully. Okay, so we've got independent and dependent. All right, and then we're going to talk about mutually exclusive here. So we've already written this one out. If A and B are independent, the probability of A and B is the probability of A times the probability of B. Now, mutually exclusive. Now, mutually exclusive means they can't happen at the same time. If you were to think of a Venn diagram, things that are B and things that happen in A and things that happen in B, there is no overlap. They are mutually exclusive. They exclude each other. If A has happened, B cannot happen. So the probability of A and B is 0. Okay, let's think of some independent events. I don't know, I wear socks and I don't know, my daughter I don't know, has cereal. The probability of my daughter having cereal in the morning is completely irrelevant to whether or not I wear socks, right? Let's try and write the word cereal properly. Then mutually exclusive events, we could look at I wear socks. All right, whatever the odds are of me wearing socks on a given day, and I wear Crocs. And this is how this should happen, because socks and Crocs are not a thing. You do not wear socks with Crocs, or at least I don't. Okay, so if I wear socks, I'm in the A bubble, it is impossible for me to wear Crocs. Now, as we've already seen here, Venn diagrams can be incredibly useful for probability because we can start seeing where different events overlap. So we've got 30 and 40 employees in a company, 30 have laptops, 25 have smartphones, 20 have both. So 20 have both. If I want 25 with smartphones overall, I've got 5 only having smartphones. And if I want 30 having laptops overall, 10 have to have laptops but no smartphones because now there are 30 people in the laptop bubble, 25 in the smartphone bubble. There are 40 people in total, 10 plus 20 plus 5 is 35, so there are 5 people without anything. And now we are up and running. What is the probability of them having only a laptop? Well, we can see straight away there are 10 people, 10 favorable outcomes. When I pick someone at random, there are 10 favorable outcomes out of a possible 40. All right, 25%. Only a smartphone. Well, there are 5 people out of 40 that only have a smartphone. That's 1/8, which probably should have checked that, but 12.5%. How many people have neither? 5 out of 40, which is again 12.5%. Now, either or, remember, or in maths in probability encompasses everything, including and. Oh, there we go. All right. So there are 35 good options for me here. 35 people have either a laptop or a smartphone out of a possible 40, which is 87.5%. Now we're going to introduce a new layer. So like I said, so far, probability, incredibly intuitive. All right. It's a language we use in our day-to-day without necessarily realizing it. We're just counting good things out of total number of things. Now, this next term is an incredibly important one for us in terms of interpreting a language, given that they have a laptop. Okay, so we're going to choose someone with a laptop, which means I'm now only looking here. All right, what's the probability that they have a smartphone? So of the laptop people, this is because there's the word given. We know they have a laptop. So there's no point me looking at the smartphone people or the people without anything. So we know they have a laptop. How many of these have a smartphone? 20 of them. Now, how many possible outcomes were there? Well, there are no longer 40 possible outcomes. Why are there not 40 possible outcomes? Because we know this person has a laptop. We were guaranteed it. We are only asking the laptop users. So that's 20 people out of a possible 30. 2/3. All right. And that is incredibly important for us, is to understand this word given. I'm not going to give us a formula just yet. Understanding this intuitively will serve us well. Let's have a look here. I draw a card at random from a pack of 52 cards. Given that the card is red, find the probability that it is a heart. Now, I'm going to give you one bit of notation here. It is, we want the probability of heart given red. Now, this looks a little bit of a fraction because it is. We want the hearts out of the red cards. So I'm picking a card. I know it's red. How many red cards are hearts? Well, there are 13 red cards that are hearts out of a possible. Well, how many cards are red? It's not 52. It is 26. And this is where this fraction, it's the hearts. Now, what we have fundamentally done here is we have looked at the things that satisfy being a heart and are red, and we have divided that by the number or the probability of red cards. Okay, so in our case here, it is 1/2. It is 50/50. Okay, and again, we are looking at this word here, given. Another word that we can see that does this sort of thing is if. If. Okay, given. Same thing. So, if on any given day I walk to the station, the probability of me driving the next day is 0.6, 60%. But if I drive, the probability of me walking the next day is 0.7. So I always either walk or drive. Given that I drive to the station on a Tuesday, what is the probability that I walk on a Thursday? Now we need to have a look at what happened. So I drove on a Tuesday, and we're going to draw something that we will look into in more detail on the next page. But from our GCSEs, we remember tree diagrams. We can draw this. It's a very good way of visualizing this and representing it. So I drove on a Tuesday. So what happens on Wednesday? Well, Wednesday I either walk or I drive on Wednesday. Now, because I know that I drove on Tuesday, the probability of me walking is 0.7, which means the probability of me driving is 0.3, right? I either walk or I drive. Between the two of them, one of these two things has happened. And then we get onto the Thursday, and either I walk or I drive. Either I walk or I drive. Now, once I've walked, the odds of me driving are much higher, right? Because I'm tired. 0.6, we've written that here, which means the odds of me walking are only 0.4. And the odds of, once I've driven, the odds of me walking, as we've established, are 0.7 and 0.3. And here we can see conditional probabilities. We will come back and answer this in a second. We can see conditional probabilities. The probabilities of me walking or driving change depending on whether I walked or drove the previous day. Now, as we may remember from GCSE, to find out the probability of me walking then walking, I need to multiply these two things together to get 0.28. Walking then driving, I multiply these two together, 0.42. Driving then walking, I multiply them together to get 0.21. Driving and driving is 0.09. And what we will notice is one of these four things has happened. I either walked on Wednesday, walked on Thursday, walked on Wednesday, drove on Thursday, etc. These will add up to 1. Now, what can we do? What is the probability that I walk on Thursday? Which are the ones I want? Well, in this case, I walked on Thursday. In this situation, I walked on Thursday. So my overall answer will be 0.28 plus 0.21, which is 0.49. Let's unpack that again for conditional probability and tree diagrams, but they are very closely linked. I've got 7 pink and 5 purple marbles in a bag. I'm going to pick 2 of them. What is the probability that I have a pink and a purple? So the first one is either pink or it is purple. Now, the odds of that happening is there are 7 pink marbles out of 10, and there are 5 purple out of 12 even. And there are 12 purple out of 12. Cool. Now, the next marble is either pink or it is purple. Right? Now, if I've already drawn a pink, there is only 6 out of a possible 11 marbles. There are still 5 out of 11. And these two still add up to 1. If the first one was purple, things change. All right, if instead I know that the first one was purple, well, there are still 7 pinks in the bag out of a possible 11. But now there are only 4 purple out of a possible 11. So the probability of a pink and a pink is I need to multiply these together to get 42 over 121. No, out of 131 even. This is 35 out of 131. Is that right? Or is it 132? I'm just being special. It's 132. Yes. That will also be 35 out of 132, and this will be 20 out of 132. Now, I want the property of having a pink and a marble. I don't care in which order. So pink and purple, I can add those two together. Hopefully, you are remembering this from your GCSE years. Nice and simple. Remember, we put the probabilities on the branches of my tree and the events at the end. Do not get them the wrong way round. Let's do another one, again similar to our previous question. A group of friends plan to watch a movie outdoors. On Saturday, 40% chance of the projector failing, while on Sunday there's a 60% chance that it will work properly. And there's a 30% chance the movie will be corrupted on Saturday and a 50% chance it will be of standard quality. Now this is where we can draw 2 separate tree diagrams. We want to compare the 2 situations. Should I watch the movie on Saturday or Sunday? Right, so let's look at Saturday. And let's even try and write the word sat in a way that is vaguely sensible. So on Saturday, the projector either works or it fails. So there's a 40% chance of it failing, which means there's a 60% chance of it working. Now on Saturday, let's ignore what happens when it fails because there's no point, right? Now on Saturday, for some reason, the file is either fine. What should we do for fine? The file is either okay or it's corrupted. Now, on Saturday, there's a 30% chance of corruption. There's a 70% chance it will be okay. So what is the overall probability of me watching the movie on Saturday Well, it needs to work, then it needs to be okay. Times those together to get 0.42. And you can also see work and corrupted will be 0.18, and the whole thing failing, so us giving up entirely is 0.4. These three blue probabilities will add up to 1. Something needs to happen. All right, let's look at Sunday. On Sunday, the projector either works or it fails, and the film is either okay or it is corrupted. So 60% chance it will work properly. So funnily enough, whether it's Saturday or Sunday, the projector works the same. And 50% chance it will be okay on Sunday versus 50% chance it will be corrupted. So I can go have a look at all my probabilities here, 0.3, 0.3, 0.4. But importantly, the odds of me being able to watch the film properly on Sunday is 0.3. So which one should I choose? Saturday. Is best. Okay, so we are our tree diagrams. I can multiply my probabilities as I go along the branch. So remind ourselves, probabilities, add to 1. Now, A dashed is not A. That's what that means. So we know that the probability of A plus the probability of not A have to add up to 1. Something's got to happen, which gives us the fact that the probability of not A is 1 minus the probability of A. We've got if A and B are independent, and only if they are independent, the probability of A and B is just the probability of A times the probability of B. If A and B are mutually exclusive, then the probability of A and B is 0. They cannot happen at the same time. And the probability of A given that B has happened, so I want all the events where B happened and A happened, so that is the probability of A and B, over, we want that out of all the B's. And there we have it. That gives you a good grounding to start tackling the UCAT probability questions.